Well, hello. It's time for some chemistry class today. So we have energy and reactions, right? We're going to look at a couple of different things today. You're going to get to see me try and write with a mouse. You think my handwriting on the board's bad? This is not going to be pretty. Um, but anyway, we're going to look at some energy graphs, try and interpret those a little bit. I've got a quick demo that we'll jump to, and then we'll kind of finish out a few things in the packet. As always, it is better that you've already done this before you watch the video on this. I'll try and move through it kind of quickly. So if you're just figuring out how to do this, if you're still struggling with this a little bit, either stop right now, go do all of them, and then come back, or at least pause me and that kind of thing moving forward. All right, so we look at this one. They gave us an energy graph, and they're asking some questions about it. So let me grab the pen tool here and get writing. Let's see. Ooh, I'll write in green. That would be kind of fancy. I'll write in green. So they want to know, is it endothermic or exothermic? Well, I see that overall it's going down. So even though we've got this bump here in the middle, overall we're releasing energy. So this would be something like a fire where, yeah, you have to add a little energy, but then the environment gets a lot more energy than the stuff that, right? The wood at the beginning has more potential energy than the ash stuff does that's in the fireplace at the end. So this would be exothermic. It is just as simple as, is the overall down or is the overall up, right? Ignoring the middle part. This is the thermodynamics part. Ooh, that sounds fancier. Therm, heat, right? Like a thermometer is a heat meter. Everyone loves the way I say thermometer. The middle part in here is the kinetics part, right? So in more advanced chemistry, we kind of focus on the kinetics and the thermo separately. We're just kind of touching on those a little bit. So what's the delta H? Delta H is just the change in reaction energy or enthalpy. If you want to be really fancy, that's the enthalpy, which is a specific type of energy. But overall, it is going down. So I know in my head this better be negative when I'm done. If I want to write out an equation, it's the products. That's a dash, not a negative. Let me turn that into an equal sign. Oh, my handwriting is awful. Equals products minus reactants. I should not do this again. So products are 20 minus reactants are 40. So 20 minus 40 is a negative 20, right? Or the way I tend to do it is I just say, well, the difference is 20 and it went down by 20. So that's a negative 20. I feel like that just makes more sense to me, right? But either way works. EA, that stands for activation energy or energy of activation. That is from my reactants up to, what's this thing called up here? That thing right there, right? That's the activated complex or the transition state. Either term is just fine. So it's that difference right there. It's how much energy do you have to add to get over the bump? Well, we're going to need to go from 40 up to 100. So that's going to be an activation energy of 60. And we can put units on there of kilojoules for both of those, but I'm not going to write either of those because, you can see. Where is the activated complex? That's this thing right here, right? That's the transition thing from reactants to products. That's when you're not dating the one person, you're not dating the new person, you're kind of dating both people. Remember, I made those terrible jokes before. That's the temporary transitional state. I'm going to do a demo here in a few minutes where you're going to visibly see one of those, which is kind of cool. Add a catalyst with an activation energy of 10 kilojoules per mole. So this is one where a lot of students will make a mistake, and I'm going to draw the mistake in first, and I'm going to draw the mistake in red because red's scary. So they say 10 kilojoules, the energy. So that's down here at 10. So I'm going to make that at 10, and then I'm going to draw it like this. Well, that's wrong because it's from reactants to the activated complex is the 10, not from 0 to that, right? Like this, we got 60 was our activation energy. So here it's 10. So where students tend to struggle is the difference between the energy of the activated complex, which that's 100 for our original pathway, and the energy of activation, right? So if my energy of activation is 10, then I'm going to go from 40 up to 50. We'll make this in blue now because blue is like not the danger color, right? In teacher school, they told us not to use red because that's like scary, right? Okay, that is really awful, but you get the idea, right? It's 10. Okay, so we do how do I go to my next slide when I'm on a thing? I don't know what I'm doing. Okay, so, whoops, I clicked past. There we go. So they give us a drawing one. Again, you should be able to do this on your own at this point. Reactants have 30, so they're going to start here. Products have 40, So that tells me this thing is endothermic. Overall, it's going up. I like to do my reactants, my products. Energy of activation of 20. Don't go to 20. Say 30 plus 20 is 50. So that's up here. And then I connect the bumps and try and make it look not like a second grader drew it, right? So something like that. It's endothermic. My activation energy is 20. My activated complex has 50. That's about all there is to that, right? So since this is endothermic, it would have to absorb energy from the surroundings. So this would be like baking a cake or something like that, right? Where you have to add energy to make it happen. Baking a cake, I guess, isn't necessarily endothermic. Well, yeah, no, that's an endothermic, yeah. Because the products have more energy than the reactants do when you start with them. Okay, so this is kind of a different one I just wanted to show you. Notice it's like there's two bumps. So this is what we call a stepwise reaction. This reaction has multiple steps. You have your reactants, you have a transition state, you have what we call an intermediate. That's a thing that you form in the middle, but then it doesn't stick around until the end. And then you form a new transition state, and then your products. So it's a multi-step reaction. There are a lot of reactions that are multi-step reaction. You might remember back to biology and the electron transport chain and the TCA cycle and all those things where you took like this chemical and changed it to this and changed it to this and changed it to this. Each one of those changes would be a bump. So you could have like bump, 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 and right. And overall, so this would be like a 1, 2, 3, however many step reaction. So you can have those. We're not going to mess with those a whole lot, but I like to show you some of those kinds of things too, right? But it's kind of neat, I think, to see this transition state here at the top and then an intermediate. That is a thing that can stick around for a little bit of time, not for a long time, but maybe for a few seconds or something like that. And before it gets used up and made into the new thing. Again, it's not a real stable kind of compound, but it's something that could stick around and then you go on from there. So a multi-step reaction like photosynthesis and lots of reactions are. Right, so we're going to go ahead and jump to a demo now, my favorite thing. All right, it's time to goggle up and do a little demo here. So we've got a couple of things. This is a redox reaction, so where electrons are changing places, oxidation, reduction kind of stuff, where electrons are going to move. In here, I have a bunch of distilled water, so to dilute it a little bit to slow the reaction down. And then there is sodium potassium tartrate. And tartrate is a big organic molecule. So lots of carbons and hydrogens. Things with lots of carbons and hydrogens like to be oxidized, right? Like sugar burns and stuff, right? So this is an organic molecule like sugar, not food, but an organic molecule. This is hydrogen peroxide. This is that 20% hydrogen peroxide. So I've got about 30% of the 30% hydrogen peroxide. Again, since I'm only doing this once, I went ahead and used a little extra, so we'll hopefully not have a big mess on our hands. So these are the reactants, and they will react just fine, but the activation energy is really high, right? Notice we've got a colorless solution right now. The activation energy is really high, so we're going to heat it up. So those molecules will move faster, right? As we heat it up, I want to heat it to about 70 degrees Fahrenheit. So we're going to heat up as it speeds up, or as it heats up, they're going to speed up and move faster. And then once it gets to 70 degrees, I'm going to add a catalyst. This is cobalt chloride. Cobalt chloride is the catalyst. Remember, a catalyst doesn't get used up. So when it's all said and done, we should still see this pink color and that kind of thing. Anything we see in the middle there would be not our reactants and not our products. And if we have something in a reaction that's not our reactants and not our products, that's going to be our transition state, right? Our activated complex. So you probably don't want to sit here and stare at my hydrogen peroxide and sodium potassium tartrate heating up. So I'm going to pause you for a second and come back when it's warm. Okay, so we are up to 70 degrees now. Remember, we're going to look at this reaction. We've got colorless. I'm going to add a catalyst to it. Catalyst is going to provide a pathway so that we can see this. All right, let's slide up a little closer here. You don't need to see me anymore. But any color we see besides the colorless and the pink is a new chemical that's formed, right? Right, so we see that new color, right? That greenish color. That's not the reactants. The reactants were colorless, and the catalyst was, Stay in there. Stay. Behave. Behave. Oh, you're not behaving. Oh, it's going everywhere. Oh, that's not too bad. Whew. There we go. And hey, I'm seeing another color change now. Now as it's finishing up, it's kind of going back to that pink color, right? So this pink color is left over from the catalyst. So that green that we were seeing there in the middle, that green was the activated complex, right? It was just there for a little while. I used a ton of chemicals because each one individual transition state is only there for a few seconds. So then it takes a whole bunch of them to see them for very long, right? So we only saw that green while the reaction was actively taking place. Once the reaction's done, that physical chemical is no longer there, right? But that activated complex isn't like an idea. It's not like an abstract thing. It is a real physical chemical that is unstable, and it's only there for a short amount of time, right? So that's an activated complex. Hopefully that helps that make sense. And I'm, again, going to put, the custodians are not going to like me. So anyway, we'll jump and do a couple problems out of the weekly packet here in just a second. All right, finishing up real quick with interpreting graph stuff, right? This is the figure 18.5, page 597 in the book, or PDF thing, whatever, however you're doing that. Right, so looking at these guys, they want us to interpret graph stuff a little bit. So we read the graphs. Is energy absorbed or released as a reaction progresses from reactants to activated complex? Well, in both these, from reactants to activated complex is just the first half of the reaction. It's right from here up. So in both cases, no matter what type of reaction is, energy is always absorbed, right? You have to add some energy to get a reaction to take place. Some of them you have to add more energy, some of them less energy, right? It takes not a whole ton of energy to get paper to catch on fire, where it takes a lot more energy to get a log to catch on fire, right? But either one of those, you have to add some energy to get them to happen. B, how are the graphs for reactions 1 and 2 different? Well, if you look here, we go from reactants to products, and it goes downhill overall. And here we go uphill overall. If you look, it actually looks like it's the same chemicals, just in reverse. Actually, AP Chemistry looks at a thing called equilibrium, where a lot of reactions, not all, but a lot of reactions can go back and forth like that, where products are now reactants and stuff. But overall, my reactants go downhill, exothermic. Overall, my reactants go uphill, endothermic kind of thing, right? Classify, I just did C. Exothermic, endothermic. And I know that because overall it released energy, overall it gained energy. So this would be a negative delta H. This would be a positive delta H. Explain why might a reaction that releases energy require some energy before it can begin. So again, that goes right back to like the fire kind of thing. Yeah, fire releases energy, but you've got to form that activated complex. You've got to form the physical chemical structure. You've got to make it, and it takes some energy to break those bonds. This is in the process of breaking bonds, right? So even if overall you're going to release energy, it takes energy to break bonds, and we have to break bonds to start reactions, right? So right here where it says, why might a reaction that releases energy need some energy to get going? Now, there might just be enough energy in the room. Some reactions are spontaneous at room temperature, right? You won't always have to heat them up. And stuff, but you still, it's still going to absorb some energy when they collide, right? E, draw conclusions. Once an activated complex formed, does it always proceed to form products? Just go to like a ball on a hill kind of thing. If I have a ball sitting on top of a hill, could it roll either direction? Sure, absolutely, right? This could roll either way if it does that, right? But overall, more of them will probably end up going towards our product side when we're releasing energy there. That's one of the benefits of a enzyme, is it actually kind of shoves it in the direction of the products a little bit. It grabs onto stuff and then physically manipulates it and moves it towards the products. Right, that is a long enough video for today. Any of the other homework problems that you haven't done outside of the thermostoichiometry stuff, you should definitely jump into a Google Meet and get some help with. But the thermochemical stoichiometry stuff, that's what we're doing Thursday, Friday.